Hello everyone, my name is Sai Nithan Reddy and today I'll be presenting my capstone project titled Air Quality and Pollution Prediction. This project was completed under the guidance of Dr. Chaoji Wang. So the main objective of this project is to use machine learning to analyze air pollution data and build a model that can accurately predict ozone levels. So I have also developed an interactive Streamlit web app that allows real-time predictions. So let me just give you a quick intro about my project. Air pollution is a growing global public health issue, as we all know. So, pollutants like NO2, SO2, CO, and especially ozone, which is also called O3, can cause severe respiratory and cardiovascular problems. So, in this project, I focused on three major goals. So, the first one is predict ozone AQI using machine learning. The second one, explore and analyze pollution patterns using EDA. And third one, built an interactive, user-friendly web application powered by my train model. So, coming to the problem statement, the problem I'm addressing is very simple. So, can we accurately predict ozone AQI using other pollutant variables? And additionally, I wanted to know which pollutant influences ozone levels the most. And can this be implemented in a real-time app for public or environmental use? So the data set, this is my data set overview. So I used the US EPA air quality system data set, which contains over 1 million rows and 29 columns, covering the years 2000 to 2016. So each row represents a daily pollutant reading from different monitoring stations across the US. So for my modeling, I selected the key pollutant features, that is NO2 mean and AQI, O3 mean, SO2 mean and AQI, CO mean and AQI. So my target variable was O3 AQI. So uh, coming to the data cleaning and pre-processing, I began by identifying missing values, inconsistent formats, and duplicate records. So missing values were handled using median imputation, and data was formatted into a tidy structure. I also converted dates to proper date-time format, sampled large chunks of EDA, and removed redundant columns. So this steps ensures the modeling stage is accurate and efficient. So coming to my EDA, so the first one that you are seeing is a histogram of O3 AQI, the first image that you are seeing now. So this histogram shows the distribution of O3 AQI values. So we can see the most ozone AQI levels fall between 20 and 15, so which corresponds to good and moderate air quality ranges. So extreme high ozone values are less frequent. So uh, the next image that you are seeing is a correlation heat map. So this correlation heat map helps us understand how pollutants relate to each other. So a key observation here is that O3 AQI is strongly correlated with O3 mean. So other pollutants like NO2, SO2, CO shows much weaker correlations. So this tells us that ozone behavior is mostly dependent on its own concentration levels rather than the other gases. So the next one is the scatter matrix. So this scatter matrix provides a deeper look into the relationships. So you will notice a clean linear pattern between O3 mean and O3 AQI. So the other pollutant shows much more scattered, weaker patterns. So this confirms that O3 mean is the strongest predictor of for O3 AQI. So the next one is the time series trend. So this plot shows the ozone AQI changes from 2000 to 2016. So we observe regular seasonal patterns. So ozone levels rise during warm months and fall during winter months. So there is no major long-term upward or downward trend, but seasonality is very consistent. So coming to the box plot shows the distribution and spread of O3 AQI values. So the median values are relatively low, but we do see some high value outliers. So these outliers represent days with unusual high ozone pollution using caused by weather or specific emission events. So I use for the model training, I trained multiple regression models to predict O3 AQI. So these include like the linear regression, ridge regression, lasso regression, random forest, high gradient boosting, XGBoost, and dummy regression as regressor as well for the baseline comparison. So we evaluated the models using MAE, RMSE, and R square. So from the results, XGBoost clearly performed the best with the lowest MAE and RMSE and the R square of around 0.77. So if you ask me why Exiboost was the best, so Exiboost clearly Exiboost like achieved the highest R square, meaning it explains like 77% of the ozone variance, 70%, 77% of the variance in ozone AQI. And also it delivered the highest R square score, outperforming traditional regressors. Also, it handles non-linear relationships in pollution data better than the linear models. So coming to the stream like web app, like I've developed a Streamlit web application. So let me just quickly show you that as well. So as you can see, the Streamlit UI works by linking the front end user inputs with machine learning models in the back end. So let me just quickly show you. So this is the interactive Streamlit app I developed. So users can input pollutant levels such as like NO2, SO2, CO, and O3 mean. So let me just, for example, I just gonna enter 25 here. Or like you can just increase the values with whatever you want, and there you go. So it shows the predicted O3 AQI up for the given values. So the app uses the trained XGBoost model to instantly predict the ozone AQI. It then displays the predicted AQI, the AQI health category, whether it is good or not. Here you can see, and also a health interpretation message, like as here you can see. So this makes the model practical and easy for real world use. So the user enters like basically the user enters the pollutant values. So the Streamlit organizes them into a data frame. So the trained XGBoost model predicts O3 AQI, and the app displays both the numerical prediction and the health category. So everything updates instantly without reloading the page. So this makes the prediction tool accessible like even to non-technical users. And let me just come back to our presentation. So this is the overview. I just shown you that. So yeah, now coming to the future work. In the future, this project can be extended by adding like weather variables like temperatures, humidity, uh, and wind speed. Like we can also experiment with time series models like LSTMs and deploy the app on AWS and Heroku. So finally, the model can be expanded to generate multi-city pollution forecasts. So in while in conclusion, like to conclude, this project successfully demonstrated like how machine learning can be used to predict ozone AQI. Also, EDA helped like uncover patterns. XGBoost developed strong predictive accuracy. Also, and Streamlit app made the solution interactive and user friendly. And thank you so much. That's all about my project.